Okay, so let's look at these identities and see what they're all about. The very top says fundamental trigonometric identities. Fundamental sounds pretty serious because it's a fundamental thing. So you need to memorize and know everything on the front of the sheet. And you're like, whoa, that's a lot. If I looked at that, I'd be going, there's no way. I'm just not going to do it. I'm going to go have a Pepsi. Watch CSI or something. Right? We'll start looking at it a little bit more in detail. You already know a third of it. Don't you already know the reciprocal identities and the quotient identities? Didn't we work with those in the last chapter? Am I right? You already know those. So those should be second nature to you. So that's nothing you have to memorize because you've used them enough that you know them. This, however, is slightly new, but it has a familiar word in there, Pythagorean identities. Right? That will clear if I can. No. That's as good as it gets. So for your Pythagorean identities, let's go back to the unit circle. I always like to know why something, how they came up with something so that I can derive it rather than memorize it. In the unit circle, let's look in quadrant 1. Would you agree that the x value, and we're going to say cosine of u, to maintain consistency here, that the x value is cosine? Agree? What's the y value? Sine. And what is the hypotenuse is the radius of our unit circle. What's the radius of a unit circle? Unit circle means 1, right? So does it make sense that they use the Pythagorean theorem to come up with this formula? Sine squared plus cosine squared would equal 1. That's where they came up with it. So I would put in here Pythag theorem. The only one that I memorize off of these is this one. I go and derive the other two. I know that the cos go together in the Pythagorean identity ones, so cosecant and cotangent, and I know that tangent and secant then must go together, and there's a 1 in there somewhere. But I don't knock out my brain with it, unless I used it every day. The more times that you use them, then you start to remember them. So instead, if I'm going to take this on a test, and I need to know these, and you will, the very first thing I do on a test, I would write this down. Is that one you should know. And then you can derive these two from that one. So then, to get something with tangent in it, take the original and derive tangent. Tangent is what over what? Sine over cosine. Well, yeah. The tangent is sine over cosine, right? So I want to have my sine squared with a cosine squared below it, because that would be tangent squared, and that's where that would come from. But if I divide one term in this equation by cosine squared, I have to divide every term by cosine squared. So to get the two different formulas, you're going to divide one equation by cosine squared. This gives you your tangent squared. Cosine squared over cosine squared gives you the 1. And then what is 1 over cosine squared? Reciprocal secant squared, right? And so that is how we derive this. How do I derive this one? What am I going to divide by this time? By sine. Because cotangent is cosine over sine. So I want my cosine that has sine in the denominator. You might want to wake up. Please. And so if I divide that by sine squared, everything gets divided by sine squared. And so this is where the 1 comes from. This is where the cotangent comes from. And this is where the cosecant comes from. So if you know this one, you just have to derive the other two. Easy. So far I'm only having you memorize one additional thing. So far, right? You can do that. Then let's look at this thing called co-function identities. That one's totally new. In some respects, your 8th grade algebra teacher might have mentioned it to you, or your 10th grade geometry teacher. But co-function identities are based upon complements. Complements of angles. What kind of angles are complementary? Angles that add up to what? 90 degrees. So if you look in just a regular triangle, right triangle, we call it A, B, and C. Let's just start with this one down here. Sine of pi over 2 minus u. U is an angle measure. You have to get used to them changing out angle measures. Instead of theta, now we're using u. They can use any Greek letter or any alphabet letter to represent an angle measure that they want to. And you're going to see in this chapter them switching it out a lot. So this just means the sine of pi over 2 minus some angle measure. And what's pi over 2? 90 degrees is equal to the cosine of that angle measure. Alright, well, let's just say for chuckle's sake that angle A represents the u angle. This angle measure u. Don't the acute angles in a right triangle add up to 90? So if this is angle u, how do I find this one? If this is u, what's this one? 90 minus u. And instead of 90, I'm going to use pi over 2. So this is where the pi over 2u is, if this is u. Then here's how they came up with this identity. Somebody realized, when they were finding sines and cosines, that if I found the sine of this angle, so let's use that as an angle of reference, pi over 2 minus u, that's angle B right here, this angle. What's sine? What over what? Opposite of the hypotenuse, so what side is opposite? AC. So the sine of this angle would be AC divided by what's the hypotenuse? AB. They're saying that turns out to be exactly equal to the cosine of the complement angle, which is u. So cosine is what over what? Adjacent over hypotenuse. So what side is adjacent to angle u? AC. And the hypotenuse is still AB. Then the cosine then the sine of this angle turn out to be the identical ratio of the cosine of this angle. Right? And that's all they're saying, and that's the same for all of these. So the cosine and the sine, and this is just these two flipped, right? It's now saying if I took the cosine of this, it would be the same as the sine of this. Cosine is BC over AB. Sine of this is BC over AB. They're identical. That happens with tangent and cotangent, and with secant and cosecant. And in our minds, we generally think of sine and cosine going together, tangent and cotangent going together, and secant and cosecant going together. So if you know that the sine and the cosine of the complements are identical, you don't have to memorize a whole lot right here. You just have to get comfortable with the fact that they're using pi over 2 minus theta or u or whatever they're using for their angle measure. And so we can replace any sine. So if I said the sine of 30 degrees was 1/2, what's the complement of 30 degrees? 60. So what's the cosine of 60 degrees? 1/2. So the sine of 30 and the cosine of 60 are exactly the same, and they are both 1/2. That's all it's saying. So we're going to use that in a bit. Then the last one here that's, again, sort of brand new to you, will be even and odd identities. Well, we've talked about even and odd functions. Do you remember what an even function graph is symmetrical to? versus odd? An even function is to what degree? Second or fourth or sixth, and what do you know about end behavior? For even functions. They go in the same direction, right? So even functions are symmetrical to what? Axis. Be the y-axis, right? Whereas odd functions, the end behavior is going in opposite directions, right? Like y equals x cubed. So odd functions tend to have odd exponents. Well, we don't see that with sine, cosine, and tangent. We don't see exponents. So it's hard for us to just identify whether it's an even or an odd function. It happens to be, oh, it's sort of off. That is hilarious. I've not seen that before. So odd functions are symmetrical to, what do you think? It can't be the x-axis, so it is the origin. So let's look at the graphs of sine, cosine, and tangent. I'm not going to do their reciprocals. And see whether they're even or odd. So sine starts at 0, up, 0, down, 0. And cosine is up, 0, down, 0, up. And tangent, I'm only going to do one period of tangent. So let's start with sine. Is sine symmetrical to the y-axis? Could you fold the graph at the y-axis and have the graph lay on top of itself? No. Right? So that means it's symmetrical to y. If you just look at this where we've restricted sine, well, the inverse sine, doesn't that look like y equals x squared or x cubed? And that's symmetrical to the origin. So this is even or odd. Yep. And what that means is it says that the sine of a negative angle is exactly the same as the opposite value of the sine of a positive angle. In other words, the negative angle and the positive angle have opposite signs, the values of their signs. And look at it this way, if I have a negative value for x and an equivalent positive value for x, in other words, they're the same number, but one's negative and one's positive, you see how this one is going to have a positive y value and this one's going to have a negative y value. That's all that this is saying, is that an x value of different signs means that the y values are going to have opposite signs. Look at cosine. What is cosine symmetrical to? The y-axis. So that means it's a what? Even. And what this is saying is whether you have whether you have a positive angle value or a negative angle value, they will both have the same y value. They both have the same secant or the same cosine. In other words, let's choose a negative value for x here and an equivalent negative value for x here. Same numbers with opposite signs. You see how they have the same y value. Or you could choose an x value and a y value that are both positive and negative, but they have a negative y answer. But they both have the same negative y answer. Okay? So you have to do the And so all it means is there's no difference between the cosine value of a positive and a negative angle. So the cosine of negative 30 degrees is exactly the same as the cosine of positive 30 degrees. What about tangent? Even or odd? It's odd because it's symmetrical to the origin. So So same thing occurs if I have a negative value for x versus a positive value for x. They're going to have the same y values for opposite signs. The same thing happens as does with sine. And it kind of makes sense because doesn't tangent and sine, didn't we take their inverses and restrict them to the same quadrants? This is one way that it helps me to remember these. So they're restricted to the same quadrants 1 and 4, so they go together, so they're both opposite values. So tan of negative u is going to be negative tan of u, so we're going to change that sign. Whereas cosine was the only one that was restricted to quadrants 1 and 2, and so it doesn't change signs. It stays the same. So we're going to use that here in a minute. So let's look at our two examples. Start here with example 1. In order to do example 1, there's an error in your notes. You need to add to this that the tangent of theta is equal to 3. You cannot complete the problem unless I tell you that. You wouldn't know that, I have to tell you that. So our job is to find the sine of theta, whatever that angle measure is, if the tangent of theta is 3, it's the ratio of the sides, and the cosine of theta is greater than 0. So step 1 is to figure out what quadrant we're even talking about. And we've done this in 2 separate occasions, 2 separate types of problems before. So look at your quadrant. This ratio is positive. Where's your converse? Are you confused? I just told you that because you can't complete the problem unless I give you that information. If all I said was tangent of theta and cosine of theta are positive, and then you'd be going, okay, I can't find the sines, I know nothing about segments. Does that make sense? So I gave that to you. It could switch. I could say this is equal to 1 or 0. I would, yeah, I have to give you something in terms of that. Alright, so tangent is positive because the ratio is positive in what quadrants? 1 and 3. And then cosine is greater than 0. They're telling you that why? Because we're saying that cosine is positive. So where is cosine positive? 1 and 4. Note that I don't have any inverse tangent in here, so I don't care about those restrictions. I only have tan and cosine. So I care about where they're restricted in terms of their signs. So where is my reference triangle going to be? And so here's where theta is. I still don't know theta, doesn't matter. I do know that this ratio for my theta is 3 over 1 for tangent. And what is tangent? What over what? Opposite over adjacent. So side opposite would be 3 and adjacent would be 1. So that's all that we can use that information for. Step 2, we ultimately are finding the sine of theta. Do I have to know the hypotenuse of my triangle in order to find the sine of theta? Because sine is what over what? Opposite over hypotenuse. So I do have to know my hypotenuse. So I'm going to label that hypotenuse C. And so we're going to find C. In order to find C, I need to square it and set it equal to the square of the sum of the square of the legs. 1 squared. If I ultimately really want to find C, what do I really have to do? Take the square root of both sides. And so 1 squared is 1, 3 squared is 9, to add to give me 10. Is that fully simplified? Yep, 2 perfect squares. So now I know C, square root of 10. So now I can find my sine. Sine of theta is equal to opposite of a hypotenuse. What's my side opposite? And then my hypotenuse is 10. So you can leave that answer unused or unrationalized. So 3 over red 10. So that's really not that much different than what we've done before. All right, let's use some identities. Look at example 2. Can I move that? So example 2 says this time if the cosine of theta is 0.41, that would be the decimal equivalency of the ratio of the sides, find the sine of theta minus pi over 2. Well, that's kind of weird looking. Have we seen that before? We just saw it, sort of. Does this look familiar at all? Does that look familiar at all? They're similar, aren't they? But they're not exactly the same, are they? How are they different? This is not the same as this. How are they different? Pi over 2 here is negative, it needs to be positive. My theta, which is u, they're interchangeable. My theta is positive, it needs to be negative. Algebraically, how can I fix that? So I can't use this identity until they look identical. So we're dividing. Rather than multiply by -1, and dividing means I'm fractioning it up. So the sine of theta minus pi over 2 is actually equal to, we're going to factor out a negative, because the factor out of the negative is going to change that theta to a negative. And it's going to change the pi over 2 to a positive. So if you don't mind, I'm going to go ahead and just switch them. Can I do that? A negative, we'll switch those around. Because now they're opposite signs. And the reason why I wanted to do that, I want this to look identical to that identity up there. So what does the sine of pi over 2 minus theta actually equal? What can I replace it with? Isaac, I'm pretty sure you haven't had this before, right? You might want to pay attention. It's not easy. And so I can replace that exactly with what? Cosine of theta. So all of that gets replaced with a cosine of theta for that identity. Do I know the cosine of theta? Yeah, they told us the cosine of theta was this, so can't I replace all of that with 0.41? So then I have equals negative 0.41, which means that my answer to the sine of pi or theta minus pi over 2 is actually negative 0.41. So one of the biggest errors that you guys make on this side is that you view this as the same as that identity above. And so you would have replaced this with a cosine of theta and said that the answer was positive 0.41. So big note to yourself, don't do that. You have to make sure that they're identical. Pi over 2 has to be first in those parentheses, and it's got to be positive. Okay? So there's our first substitution of one of our identities. Then, flip it. We're going to start to learn how to simplify and add and subtract fractions that have true functions in them. So, look at this one. When I say simplify, I mean for you to break it down to its most simple form. Right now it looks a little complicated. The most simple form would be like perhaps not a fraction or just a single monomial term. You're going to wonder how did you know to do that? How did you know to do that? I don't know how to do that. Think to yourself some strategies. Some strategies that you want to employ would be always break things down to sine and cosine, if at all possible. If things are factored out, multiply. Or if things are not factored, you might want to factor. I will not convert things to tangent and cotangent unless I absolutely have to. Sometimes it's necessary. But more often I'm trying to convert things into sine and cosine. So we have the secant here that I want to deal with. I like the sine squared, perfectly okay with that. But that factoring pattern should look familiar to you. If I replace the secant of x with just an x, and we just have x plus 1 and x minus 1, what is that? Difference of two squares. And can't you multiply that together? And so that's where I would actually start. So we're going to actually multiply this. So you're going to multiply the first, which is secant squared x. The squaring goes in between the secant and the x, and it's raised like an exponent. The x does not get squared. We're not doing x times x and secant times secant. The x and the secant are not multiplied together. It's one whole unit. But if you put the squared here, it looks like we're taking the secant of x squared. And that's completely different. So your power to that trig function has to go in between them. And then minus the second one squared. What was that? Because this is not secant times x. It's the secant of x. It's one combined thing. So we're really squaring secant of x, and the x is part of that. So the whole function, secant of x, is actually squared. Technically, you could look at it as secant of x squared. Because it's a pain. And more often you'll see it written this way. It's just more writing. I don't know. And then all of that is still over sine squared of x. Anytime I see anything, yes. Because the difference of two squares factor pattern, a plus b, a minus b, that factors as a squared minus b squared. Right? Are we all good to this point? Because if you don't understand something, you've got to ask if somebody else has that same question. You have to stop. Well, I'll just keep going. Yes.
The secant of x squared is on the top. Is it like
Oh, somebody was asking me why did I write the secant of squared x this way? Technically, you could write it this way as well. Because my point is, it's not secant times x, so when we multiply secant of x times secant of x, we don't get secant squared x squared. And I definitely don't want to put the squared here, because it looks like I'm taking the secant of x squared, which is something totally different. So you could either write it this way, or this way. This is more the thing. So secant squared minus 1 squared. It's technically what we just did. Anytime I say anything squared, warning bells go off in my head. Ding, 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 ding. Why? I'm trying to simplify. Keep replacing values with better values. I could replace sine squared with something, but it wouldn't do me any good. Because what does sine squared here equal? If I were to get sine squared by itself, what would you have to do to the equation? Get sine squared by itself. How do you get rid of cosine squared? Subtract. You absolutely do. So sine squared would equal 1 minus cosine squared. Well, I could put that here. That doesn't do me any good though. Then I'm kind of stuck. So instead, do I have a value for secant squared x minus 1? Well, here I see a secant squared, right? Can I make this side look like secant squared minus 1? How? Subtract that 1. If I subtract that 1, it goes over here as secant squared minus 1, doesn't it? What does that equal? Tangent squared. So you have to be able to manipulate these formulas any way that you can. Each of these formulas will give you 3 different formulas. So like this one, this is one form. Then another form would be to get the tangent squared by itself. To get tangent by itself, you'd have to subtract the 1. So you get secant squared, I guess I'll use a u, minus 1. So that's another form of that same equation. You have to be able to manipulate them. Then if I wanted to get the 1 by itself, what would I do? Subtract the tangent, right? So I'd have secant squared of u minus tangent squared of u. So if I ever have secant squared and tangent squared in the same problem, I will manipulate it, if I can, to get this so that it has a value of 1. And I could replace this whole thing with just a value of 1, which really simplifies things. And I can do this for this equation and for this equation. So you really have 9 equations in 1. Or in 3, I guess, however you want to look at it. So you have to be able to look at those and go, okay, can I change that or manipulate that to suit my needs? And so that's what we're going to do here. So we're going to take this entire value here and replace it with tangent squared of x. We're still over sine squared of x. So I have part of what I want. I said originally I like to change things to cosine and sine. So I have sine. Can I change tangent into cosine and sine? Yes, I can. Well, to do what? What happened to minus 1? Remember this entire value? I changed this formula here. I subtracted the 1, so the entire value secant squared minus 1 equals tangent squared. So when I change that and put the minus 1 over here, doesn't tangent squared equal secant squared minus 1? So I can replace, and I have to replace secant squared minus 1 with what its value is, tangent squared. Right? Can I subtract 1 from both sides? Right? Minus 1, minus 1. Did we just do that up there? Are you okay with that? So that means that whatever's on the left side or the right side, those are what I can switch out equally. So because I have on the right side of my equation, secant squared x minus 1, I can switch it out for tangent squared. They're equal. Are you just saying okay? Because I can do it by hand up here. You sure? Yeah. Okay. Then I'm going to do another substitution with this. What can I substitute out for tangent squared? I don't want to substitute this back in. So what can I do instead? Think simple. What else is there for just plain tangent? Sine of a cosine. Well, this is tangent squared, so that's no different than sine squared over cosine squared. So I'm going to replace all of its tangent squared with this, mostly because I know I have a sine squared here. So that's all over sine squared of x, and you're thinking, why would you do that? Because now that made that more complicated. Not yet. Give it one more step. We have a fraction and a fraction. What do we normally do? Take the numerator, sine squared of x over cosine squared of x, and do what? Multiply it by the reciprocal of the denominator. So that reciprocal would be 1 over sine squared of x. Do you see why we did that now? What can I do? I can cross cancel both of the sine squareds, and I'm left with 1 over cosine squared of x. Still not fully simplified. What's even simpler, it's a proper word, than this. Secant squared of x. Done. So this entire thing here simplified to just secant squared of x. More work is preferred over less work. If I cannot determine how you went from one step to another, I will mark you off. If you don't use viable substitutions, if I can't follow how you did it, I will not just be grading your final answer on these. I grade your work as well. So I have to be able to see your thought processes.
So,
Nick, go first.
did you take the reciprocal of sine squared x? That's what it's not for.
Correct.
So,
Yep, I took this reciprocal here.
yeah.
Question?
Why would you do that into the calculator?
Why would I need what?
Into the calculator?
Why would I need this unsimplified version? Because you might start with this and have to get down to this.
Well, I understand that, but I'm like, why would you do that too?
Well, we're building. Because you're next going to solve equations. In order to solve equations, you might have to simplify down to something in order to solve an equation.
Yep.
And then we have application problems, which is where they come into play in real life. But before you can actually use them in real life, i.e. engineering and et cetera, you have to know how to solve them first.
So this is your secondary user?
A lot of trig is used in that one. It's also used in engineering, various engineering fields. Okay, so that's done. Before we can go on to example 5, we have to talk about factoring, and this is where you need your own sheet of paper. because there's not nearly, is that mine or yours? Sorry. There's not nearly enough room on here for you to be able to show all of your work. So we're going to do example 4 on a separate sheet of paper. That's all we're going to try to squeeze it in there. And the directions tell you to factor. And it's important that you realize the difference between factoring and simplifying. Because we start off with A being secant squared theta minus 1. That looks very similar to what we did here. What I don't want you doing is substituting this in for tangent squared, because that's a substitution, that's not a factoring. There's a difference. We're factoring this time. And there'll be some reasons to our madness just a short in a minute. If you don't like looking at secant squared, you can instead let x equal just plain secant of theta. And if I replace secant of theta with x, I'm really looking at x squared minus 1. How do I factor that? It's the difference of two. We're factoring. So I'm trying to make it look simple. Some people don't need to do this substitution. You can factor this to our final answer without, but for some people that they don't want to look at it that way. So instead you could choose, I'm not making you, but you could choose to replace the trig function with just an x. But you have to resubstitute back in everything. So isn't this the difference of two squares? Doesn't that factor as a plus b times a minus b? And so we have a plus minus pattern. The x squared becomes x and x, and the square root of 1 is 1. But that's not my final answer if I substitute it. I have to resubstitute back in the value for x, and we let it equal secant of theta. All I can say is my son had better have gotten my dog to the vet today. I believe it was happening. That's my answer. So now I'm distracted. Yes. Because the direction said to factor. They didn't say simplify. If the directions had said simplify, you would have had one step. We would have replaced that with tangent square of x or theta, and we'd be done. So there is a difference between the directions of simplifying versus factoring, so do know that. All right, so let's look at B. And B is sine squared theta plus sine of theta minus 6. Again, you could factor it without substituting, but this one's now a little bit more complicated than A in the sense that we have two signs in here, but you want them to be the same trig function, which is fine. So you could choose to let x equal what? Just sine of theta. Because then that means this one becomes x squared plus x minus 6. And this is an easy factoring problem. What factors of 6 subtract to give you a middle term of 1? 3 and 2. The x squared becomes x and x. What does the sign of the 3 have to be? It has to be positive, so what's the sign of the 2? It has to be negative for you to get a sum of 1 and a product of negative 6. So then we have to resubstitute in for x the sine of theta plus 3 and sine of theta minus 2. There's your answer. You okay with that? Just using our skills and using trig functions. All right, let's look at C. C is the more difficult of factoring. So you got 4 tan squared of theta plus tan of theta minus 3. So the good news is both terms have tan of theta in it. So that's what we're looking for. But if you choose to use substitution, you would let x equal what? Tan of theta. So then you end up with 4x squared plus x minus 3. So that's more complicated because we have a coefficient in front of x squared. If you don't know how to factor, you can always revert to doing what? The quadratic formula. The opposite of b, plus or minus squared, right? That one. Or instead, take your bookends, 4 and negative 3, and multiply them together. That gives you a negative product of 12. So because the product is negative, we are subtracting the factors of 12. We are looking for a middle coefficient of positive 1. So what factors of 12 subtract to give me 1? 3 and 4. The sign of my 1 needs to be positive, so the bigger of the two gets that same sign. What does the sign of the 3 have to be? Negative. So this is not quite so simple as B. We have to take the middle term here and replace it with negative 3x and positive 4x. So we have a 4x squared minus 3x plus 4x minus 3. Group the first two and group the second two. What is the greatest common factor of the first two? X. So factoring x out in front, what are you left with? 4x minus 3. What's the GCF of the second group? 1. There is no GCF, so it's 1, and if I were you, I would factor out a 1. Yes. No, you would do the same thing. And so I end up with 4x minus 3. What you have in your parentheses should always be the same, which they are. So then you're going to factor that, which is the same, out in front, and pick up the garbage, that's the GCFs you pulled out in front, and throw them in the empty bin. But we're not done, because we reset it. Replace the x. So we have 4 tan of theta minus 3 times tan of theta plus 1. That is our answer. You okay with that? So you might, Sarah, have this one in front. Because you probably have the x in front. Maybe. That's fine. All right, let's do the last one, D. So the last one is cosecant squared of x minus cotangent of x, minus 3. Why is that an For the first time, these are not the same trig function. So we have to do something to make them the same trig function. We either have to substitute something in for cosecant of x or for cotangent. When you're looking to what to substitute, look, are there any substitutions for cosecant that involve cotangent? Or are there any substitutions for cotangent that involve cosecant? What do we see? Anything up there look promising? What might look promising? That one has not only a cosecant squared in it, but it also has a cotangent, which would be really nice, right? The only thing that has cotangent in it would be this one, doesn't have a cosecant. This one doesn't have a cosecant. Does anybody else have an idea about what they might want to use? And I'll tell you why it might work. All right, so this is why we're choosing this one, because it's cosecant squared and it also involves cotangent. Isn't this already solved for cosecant squared? one side. So I can replace the entire cosecant squared with all of that, 1 plus cotangent squared. So that's what we're going to do. So all of this gets replaced with 1 plus cotangent squared of x. Then we have minus cotangent of x minus 3. Is anybody unsure of what I just did? You okay with that? This is a equal exchange right here. You have to put 1 plus in there. Then, still doesn't look like something I can factor. But can't I collect like terms? The 1 and the negative 3 and write this in descending order? So we would have cotangent squared x first, minus cotangent of x. 1 and negative 3 gives me negative 2. Now I want you to factor that. So you factor that on your own. If you want to substitute in, I would not substitute, well, you could substitute in for x. But it already has an x in there. So I would probably say that y equal, what would you like y equal? What would you like y equal? You're going to substitute cotangent of x. So you could substitute in if you wanted to. You could just factor the way it is if it doesn't matter. And then when you get your factor, check. Go up and see the root. Okay, so let's look at our solution. Here's the solution. Oops. Right here. So I let y equal the cotangent of x. So I had y squared minus y minus 2. And then the factors of 2 that subtract to give you 1 would be 2 and 1. And your signs have to be negative 2 and positive 1. Y squared becomes y and y. And I just replace y back again with cotangent of x. Yes?
So, unless there's a let's call it remove like an example x, since it's just secant, you need to, for the rest of them, you need to find to make it the same.
Yes. Yes.
And then, how to do it without like,
You have to just say, okay, this is squared and that's, or I'm sorry, this is squared and that's not. So what factors of 2 subtract to give you this? You just ignore the fact that you have it in there. I mean, you could just use cotangent. A lot of people do. Usually people use it. Don't pack up because I'm not done. I have another problem to do. So there's no packing up. You're making me nervous. So you can talk about that and then finish the last problem. So let's go back to our notes and finish that last problem. I want you to cross out example 6. Ms. Strang and I made an executive decision that we're not doing examples 6 and 7 until after the winter break. So we're going to add and subtract fractions. What do you need to have to add and subtract fractions? So we have to find the LCD. When you find the LCD, one of the reasons why we're factoring over here is you have to have fully factored denominators. This denominator, 1 minus sine of x, is fully factored. I can't do anything with it. So that's one of my factors that goes in my LCD. You have one of each different type of factor in your denominators. And then whatever that factor is, you raise it to the highest power that you have. Well, this is we only have one of these. Any monomial by nature is already factored. So I have to add in the cosine of x. So this becomes my LCD. What does this need to look like that? So I'm going to multiply this by cosine of x and this by cosine of x. What does this one mean? 1 minus the sine of x. And 1 minus the sine of x. So then we're just going to multiply. So cosine times cosine, cosine squared of x over the LCD. And then plus, I want you to understand that we are multiplying through a negative sign of x because that's what's in front. So I'm putting a plus here. And negative times a positive makes a negative sign of x. Negative times a negative is a positive sine squared of x over that LCD. Since they're the same denominator, I can combine them as one fraction. And these I'm going to put together y. What does the cosine squared of x plus the sine squared of x equal? What does it equal? You put your identities up the front. Isn't this Pythagorean identity? What does that equal? 1. So hold that thought.
Pizza.
We're almost done. So if that gets replaced with 1, now those can cancel because they're the same, which is 1 over cosine of x, which is what? Secant